So now we're going to look at the finally completely correct expansion or series for inverse tangent of x. It's the sum from n equals 1 to infinity of negative 1 to the n minus 1, x to the 2n minus 1 over 2n minus 1. And of course you could see that x equals n equals 0 to infinity, and then it would be just n here, and these would be 2n plus 1s. All right, so you can do it from n equals 0 to infinity if you want. So what's cool about that is, again, you can ask the question, what happens when x equals 1? Because something pretty interesting happens. So then over here, I'm going to have sum from n equals 1 to infinity of negative 1 to the n minus 1. I'm going to put 1 for the x, so it doesn't matter what the exponent is, because 1 to any power is still 1. And then I have over 2n minus 1, and that equals the inverse tangent of 1. So what's cool about that is not, like this one where we don't know what the inverse tangent of 0.5 is, so we can use this series to estimate it. We do know what this inverse tangent of 1 is. The inverse tangent of 1 is what? What is it? That's right, it's pi over 4. All right, so what's cool about that is that we can multiply the 4 to the other side of this equation and get this. 4 times the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over 2n minus 1 equals pi. So what this is it's a series way to calculate pi. It's a way of calculating digits of pi. All right, so pi equals 4 times, and then we could add up the series of this. So when I have n equals 1, I'm going to have 1, I'm just going to have 1, and then I'm going to have minus 1/3, plus 1/5, minus 1/7 plus forever. That gives you pi. So you can use that as an iterative method to calculate pi. So I put that in my calculator here. So I put 4 times the sum of, and I started from n equals 1 to 13, and you can see that I did negative 1 to the n minus 1, and then I just put 1 over 2 to the n minus 1 power, 1 over 2n minus 1. All right, so that's just the same thing that I have here. So since I have this times 4 in the front, what I get should be pretty close to pi. So I'm doing 13 iterations. Let's see how close to pi I get. 3.218. Oh, that's pretty bad. All right. So let's try more iterations. Let's just go right to let's just throw it to 100 right away. So 100. So this is 100 terms of this series right here converging to pi. It's thinking, and look, it's terrible. It's 3.13. So this iterative method of calculating pi, I wanted to show it to you because it's cool. It's probably one of the first ways you've seen as a way to actually calculate pi. So when people say, how do they calculate digits of pi? One thing they can do is take this sum and just keep adding it up, and you're calculating. So far, we've got 2 of them. We've got 2 digits of pi by summing 100 terms. So the drawback of this method, of course, is that it's really, really, really slow. So it's not a rapid convergence at all. And in fact, if you think about how quickly this series converged to inverse tangent of 0.5, we got to within 5 decimal places in 7 iterations. All right, to get 10 decimals of accuracy, we only had to do 13 iterations, 13th partial sum, the 13th partial sum. But here I can do 1,000 iterations of this one and make my poor calculator just sit there calculating pi for 1,000 partial sums of the slowest series that there could possibly be to calculate pi. And it illustrates something interesting, which is that the reason that we converge so quickly on 0.5 is because 0.5 is well within the interval of convergence, whereas 1 is at the endpoint of the convergence. We used x equals 1. So the endpoint of convergence. So basically, the farther you get from the center of convergence, the slower it's going to converge. So I got 3.14. If I round it, right, if I round it up, 3.141, I've got 4 digits of pi now. But it took 1,000 iterations to get 4 digits of pi. So it's a really slow process because we're at the endpoint. But by the way, speaking of being at the endpoint, the convergence interval was negative 1 to 1. And on on this series, I've convinced you that the series still converges at x equals 1, even though that's not in the original interval of convergence. Because at x equals 1, this is the alternating harmonic series. The same thing happens here. At x equals 1, this series still converges because 1 over 2n minus 1 is a decreasing function. So by alternating series test, and the limit of that function is 0. By alternating series test, because it's an alternating series, the series converges. But since, so really on both of these, the modified interval of convergence, the interval of convergence that we get is including the 1. But since we're as far away as you could possibly get from the center of convergence, it's converging more slowly. We saw it converge more rapidly when we're close to the center of convergence, and we're going to see that sort of play out as we look at more power series going forward.